Hello, Year 7. Today we're doing about balanced and unbalanced forces. So here is today's work. All I need you to do today is make sure you write notes as we go through the PowerPoint, and at the end you will have 4 diagrams to draw and a little extension question. So let's get started. First of all, what I need you to do is watch this video that's on this slide here. Okay. If you can't see the video on the PowerPoint, at the bottom here, if you exit the slideshow, here is the YouTube link. Okay, it's about a film called Gravity. I want you to look at the clip. I'd like you to tell me what kind of forces are acting on them, and also, at some point, the woman, Sandra Bullock, in the spacesuit, she starts spinning off into the distance. Now, why doesn't she slow down? Why doesn't she stop spinning? I want you to think about those kind of things. Once you've done that, go on to the lesson objectives and have a quick read of them. Okay, so hopefully you've paused this, you've gone to watch that video, and then you're back on here again. Now, back in the day, someone called Aristotle said that for something to move, there must be a constant force acting on it. Now, he was wrong, but it's understandable why he thought that, because they only really had chariots, and that was kind of the fastest moving object they had. He had a dude stood in the air with a spear or whatever, and the chariot pulled them round. So when they did the races, if the horse fell over or got detached and ran off, the chariot would stop. Now, so he couldn't see. You couldn't see the forces, right? So we couldn't see that forces were at play. Back then they didn't understand them. But someone called Galileo came along and said that objects would keep moving unless they were acted on by a force. For example, friction. So if I threw a ball in space, it would go on forever. Or if I throw a ball on the planet, it would go on until it hit something. Now, just imagine we're in space. So let's just say, yeah, there's your spaceman. You're a spaceman with a ball. Okay. If Aristotle had been right, what would happen is if I was in space and I threw the ball, it would eventually stop. That is actually not the case. We know it's not because we actually have things that are orbiting our planet at all times, right? We are orbiting the sun, the moon is orbiting us, the International Space Station is orbiting the planet, and so are loads of satellites. If they just happened to stop in space, they would fall down to the planet and crash into us, which would not be good. Now, later on, someone called Isaac Newton came along, and this is named his first law. He basically said objects will continue to move in a state of constant velocity unless acted on by an external force. Now, what that's saying is if I chucked the ball in space, it will continue on forever unless something stopped it. Okay, so there's the ball, and it should just keep going on forever unless another force acts on it. Now, so another reason why, I don't know if you've ever seen films, if you've watched any space films, they go out, if they have to go outside of the space shuttle to like do some repairs, they will usually strap themselves onto the side of the spaceship, because if they don't and they get knocked, right, they will just float off forever into space, which would not be very good for them. Now, another thing that Newton said, and this is easy to think about if you ever have played with a medicine ball in PE. If you've ever tried to throw a medicine ball to somebody else or catch it, what you'll feel that when you throw it, the ball actually pushes you back. So this is Newton's third law. What he's saying is every action has an equal and opposite reaction. Well, it's the reason why you're able to sit in a chair right now and not fall through it, but if you ever, again, movies, you've seen why guns have recoil. You see someone shoot a gun and it goes backwards, the bullet goes forwards. Okay, so here, the astronaut throws the ball's going to move away, and so is the astronaut. Okay. Another thing that's been happening recently quite a lot is SpaceX have been launching rockets up into the atmosphere and trying to get them to land, just to test them. The way a rocket works is it essentially throws fuel out the back. The fuel, they ignite it, the fuel expands, and it throws particles out the back to try and push the rocket up because of Newton's third law. Now, so you can use the third law to stop the astronaut from moving, right? So if you're moving along, okay, sorry, I'll do that again. If you're moving along and you've got a ball, you can use Newton's third law to push yourself away, which could slow you down and throw the ball off at a faster speed. This is exactly how people who throw the javelin do this, or people who do shot puts, or if you've ever watched the Olympics, they'll take a run up to the line as fast as they can and then throw the spear as far as they can. Now, what they're doing is using the increased speed, and then they throw the spear, which pushes them back a bit, but pushes the spear forward a lot, and then they see if they can throw it as far as they can, and of course, you know, the person who throws it the furthest wins. Again, if you throw the ball too hard, Newton's third law, it'll push you away, okay, and you'll fly off into space. So, let's look at the example of a car. So at the moment, this car is moving at a constant speed because the drag force and the drive force are equal. Now, what happens is if there is no no reaction force from the floor, the car starts to fall. Now, this is an equation we kind of need to know. So if you could just write that down here. Newton's second law, force equals mass times acceleration. Okay, if there is no net acceleration, there is no change in speed. Now, while the drag force and the drive force are equal and opposite, the car will move at a constant speed. Okay, as soon as the car drove off the cliff, the reaction force and the weight force were not equal and opposite, and the car fell down to the ground. Let's do another one. Car on a road. Now, we've looked at unbalanced forces. This time, the drag force is this side. So the drag force is pushing the car backwards, trying to slow it down. The drive force is pushing it forwards. Okay. Let's say they increase the drive force. The car will accelerate until the drag force is equal and opposite. Then that car has reached a new top speed. Then, let's say they brake. The drive force gets smaller. The car will decelerate until, again, drag force and drive force are equal and opposite. Okay, so let's just do that again. If you accelerate the car, so you increase the drive force, watch the drag force. It starts to increase as the car gets faster until, again, they're both equal and opposite. The car is now at a new top speed. Then the person has to brake a little bit. Drive force decreases, so the car will slow down until, again, both equal and opposite. So, very quickly, I'd like you to have a think. Situation 1, what's happening to this car? Is it stationary, moving with a constant speed, accelerating or decelerating? Well, hopefully, because you could see that there is no drive force and no drag force, it has to be stationary, because if the car was moving, there would be a drag force from air resistance. Let's go into situation 2. So how about this one? Well, you should see that the reaction force and the weight force are equal and opposite, and the drive force and the drag force are equal and opposite too. So what will it be? Well, it has to be moving with a constant speed, because the resultant force equals 0. If I was to add the 2 blue arrows together and the 2 yellow arrows together, that would add up to 0. So it has to have a constant speed. Now, situation 4. Well, blue arrows are still equal and opposite, so the reaction force must equal the weight force. But in this case, our drag force is a lot smaller than our drive force. So what's happening here? Well, hopefully you got that this car is accelerating, so it means it's speeding up. The resultant force is not zero. The blue forces cancel out, but the yellow forces do not. This drive yellow force is bigger than the drag one. So overall, there would be a net force or a resultant force going to the right, which means the car would accelerate. Let's do 4. And this is the last situation that we've got, so hopefully you would get this one. Again, the blue forces are balanced, but the yellow ones are not. The drag force is much larger than the drive force, so this will be decelerating or slowing down for the same reason. Now, I wanted to draw force diagrams, which we've done before. I'm going to... Here is your task. When I'm drawing the car, I like to draw a square. Okay, you have got 4 situations here. I would like you to draw your car at rest. Okay. Car 2 is moving forwards at a constant speed. Car 3 is accelerating and car 4 is decelerating. Now each diagram should show all of the labelled forces acting on the cars. Question 2 is explain why all cars have a top speed. Now, for an extension if you want to, a car which was moving at a constant speed drives off a cliff. Explain in detail what happens next in terms of the motion of the car and all the forces involved, and include diagrams. So I'd like you to pause now and have a go at these 4, please. So I'm going to exit this PowerPoint. Okay, so hopefully we have managed to attempt 4 of them, and now we've resumed the video. So let's make my pen pink. Now, question 1, so I should say car 1. We said car 1 is at rest, so let's do car 1 up here. And just to jog our memory, it was at rest. That means not moving, okay, stationary. Car 1, so here's my box. If it's not moving or it's at rest, then there'll be no drag force and there'll be no drive force. I'm not even going to draw them on. Now let's do weight. Let's do the vertical forces in green. So weight and my reaction force, okay, are equal and opposite. So that's car 1 that is at rest. Let's do car 2. Car 2 was constant speed. So constant speed. So let's draw my car again. And I'm going to do the vertical forces in green. Now, because it's moving at a constant speed forwards, well, I know that my weight force and my reaction force have to be equal and opposite. Yep. Now let's do my drive forces in yellow. Now if we're moving at a constant speed, the drive force, which I'm going to call P for push, and the drag force I'm going to call D for drag, okay, have to be equal and opposite because this is at equilibrium. What that means is if I add all these forces together, all the forces will equal 0. Okay, there will be no resultant force. No resultant. Right, let's move on to car 3. So let's do a line in the middle. Car 3 is accelerating. So here's my car. Let's start off with my weight and my reaction, and by now I think you understand if the car is not moving upwards or downwards and it's sat on something like a road, the weight force and the reaction force have to be equal and opposite every single time. Otherwise, either the car is falling through the road or is flying off into the sky. So let's do the yellow forces. Now we said this car is accelerating, and let's just say that the push force is this direction. push. Well, if it's accelerating, the push force has to be bigger than the drag force. Okay. So this is an accelerating car, and what you'll find is the resultant force. If you add all these forces up together, okay, well, these two cancel out, so there's no force going up or down, but these two do not. You'll find that there is the push wins slightly. This will be the resultant force, okay? The resultant force will be going to the right, which causes the acceleration, okay? Imagine this is 10 newtons, and this is 3 newtons, okay? The resultant force in this case will be 7 newtons to the right, because they cancel each other out, but 10 is bigger than 3, so 10 wins. So the resultant force in this case is to the right. Right, let's do 4. Car 4 is decelerating. Okay, so let's draw my car. Let's do again the green forces going up and down. So this is the weight. This is the reaction from the road. Now, if this car is decelerating, which means slowing down, okay, well, there's my drive force or my push force. If this car is slowing down, the drag force must be much bigger. So let's have a look. What's the resultant force? Well, let's just say that the push force is 10 newtons again, but this time the drag force is 15 newtons. The resultant force equals minus 5 newtons, or you can say the resultant force is that way and it's 5 newtons. Right? So that means this car has to be decelerating. Now, explain why all cars have a top speed. Each car has a maximum push that it can have, okay? Eventually, let's say you've got a perfectly flat road and you've got a really straight line going on forever. If you push at maximum force, your car will go faster, and as your car goes faster, the drag force increases. So, let me file. Let's just do new. There we go. Do not save. Right. So let's say I've got my car. Here it is, and it's pushing at maximum force. As time goes on, say I'm starting at stationary, I start moving a little bit, my force is this big, I get a bit faster, the green force gets bigger, I get faster, the drag force keeps getting bigger and bigger and bigger until the drag force and the push force are the same size but in opposite direction. So the car has got a maximum push. If you need more push, you'd have to get a bigger engine, okay? So every car will have a maximum top speed because eventually the push force will equal the drag force. Now let's do the car driving off a cliff. So there's my road. Let's do the road in blue. Right, and there's my cliff. So start off, my car is here, driving, like in the movies, and then it's here. We will do, again, well, there's my weight force, and there's my reaction force. Constant speed, so my push force is equal to my drag force. I go off the cliff. Let's just say that my push force is equal to the drag force. It wouldn't be that because my wheels aren't touching the floor, but let's just say it stays the same just for simplicity's sake. Now, my weight force is still pulling downwards, but there is nothing to push me back up. Here's the ground or the road or whatever, or the cliff. Well, if I was moving at a constant speed here, my resultant equals 0. Resultant equals 0. But now, let's say that my car is 100 newtons. My weight of my car is 100 newtons, which is a very light car. There is nothing opposing this force. So what happens is, the resultant force is downwards. This car will accelerate. And then it sort of falls straight down to the floor and breaks. Now, once that's everything that you need to do for today, just email me your notes and then you are done.